Hey everyone, we're going to talk about a correlation today. This begins the topic of regression. And when we talk about regression, we're trying to understand the relationship or the association between two variables. And these two variables will have to be quantitative variables for the methods that we're going to talk about here. Okay, so things that are going to come up would be we're going to talk today about drawing and interpreting scatter diagrams. We're going to let the computer do that. We're not going to actually draw them by hand. We're going to talk about the linear correlation coefficient. We're going to compute that, not by hand, but on a computer. And we'll start out by introducing this data set here that's in our notes. This data set deals with golf balls. Recorded as the speed of the golf ball and the distance the golf ball traveled. So these are both quantitative variables. And you would imagine that there's an association between the speed, not the speed of the golf ball, sorry. It's the speed that the club is when it hits the golf ball. And the distance the golf ball travels, I believe that distance is in yards. Okay, so the speed of the golf club and the distance that the ball travels. And so you can imagine that there should be an association. The faster the speed of the golf club, you would think the further the distance the ball would travel. So this, we'll deal with this data set quite a bit throughout this whole chapter to examine and quantify the relationship between these two variables. And so these variables are what we call pair data because they occur in pairs. And so the speed, each speed is matched to a particular distance. So these values are paired. You can't mix this up because they're paired with these observations here. So the speed of the golf club at 100 represented a distance of 257 yards, this paired data that was recorded on these. So we're going to first talk about what we call scatter plots or scatter diagrams. And these are made on an X and a Y axis, and each pair of observation represents one dot on the scatter plot. So you'll have one dot at X is equal to 100 and Y is equal to 257. Okay, so there should be 8 dots on the scatter plot that we're going to create. And the scatter plot is right here. We put speed on the x-axis, we put distance on the y-axis, and we did that for a reason, but we'll explain the reason a little later. We're not going to talk about that right now. If I wanted to create a scatter plot in StatCrunch, I can do that. So here I've entered the data into 2 columns, and it's a graph. So I go to Graphics, and then I go to Scatter Plot. That's what the graph is called. The scatter plot, the book calls it a scatter diagram. And just select it, and this is quite easy. I put speed on the X, distance on the Y, and I could just click Create Graph. I'm going to try doing something else. I'm just going to put a linear line over that just to show you something. And that's all I'll do. I'll do Create Graph. Okay, so here's the scatter plot you see in your notes. And the computer drew a straight line that looks like it fits the data pretty well. You can see some of the distances are above the line and some are below the line, and the line kind of splits the difference there. So this line, if we could quantify that or create an equation, would be useful in describing the association between speed and distance. Okay, so let's go back to the notes. A couple things we want to look at when we look at a scatter plot. We want to identify whether there's a linear association or a nonlinear association. I just realized I skipped part of this. The first thing we want to look at is direction. We want to know, describe whether it's positive or negative. Positive means that as one variable increases, so does the other. So you'll get that you'll get a line that goes in a positive direction. And that makes sense. As the speed increases, so does the distance. So this would be a positive association. A negative association would mean that as speed increases, distance decreases. So you would get a line that slopes in the negative direction, so decreases from left to right. All right, so this is a positive association. That's what goes in that fill in the blank right there. Okay, the other things we want to look at are whether or not the relationship is linear. So linear means it follows a straight line. Nonlinear means that you might have a curved association. So if you couldn't really fit a straight line like we just did. So if I go back here, this is definitely a straight line fit. A curved fit would maybe look more like this. And that, for this example, doesn't really describe the relationship. So here we have a linear association, but a lot of times we'll have a nonlinear association. For our particular example, the answer would be yes, it does appear linear. Another thing we like to describe is what we call scatter or strength of the association. So let's go back. And you can see the points fall pretty close to the line. That means there's a strong association. That means that speed is strongly related to distance. So if you know the particular speed, you can make a good prediction about the distance. If the points were further away from the line, so there's more scatter around the line, then the association would be weak. And so we describe associations by weak, moderate, or strong. In this case, I would call this association fairly strong because the points fall pretty close to the straight line. However, you might want to actually quantify that association. So we can put a number that describes the strength of the linear association, and that's called the correlation coefficient. You calculate the correlation coefficient using the small letter r. That's how you denote it. And this is the formula for the correlation coefficient. And I'm sure at this point you're happy to know that you will never have to do this by hand. But what the correlation coefficient does, it describes the strength of the linear association. And the correlation coefficient can be positive or negative. If it's positive, that means the association's positive, and if it's negative, the association's negative. And the correlation coefficient's always between 0 and 1. And so it's between -1 and +1. If the correlation coefficient's equal to 1, there's a perfect positive association, means that values fall along a straight line. If the correlation coefficient's negative, there's a negative association, meaning the values decrease from left to right. If the r is equal to -1, then the points fall right on a straight line. If r is close to 0, means there's really no evidence of a linear relationship between the two variables. And another fact about the correlation coefficient, it's unitless. So if you're looking at inches and convert it to feet, then the correlation coefficient is unchanged. Okay, so let's go back to StatCrunch and look at the scatter plot again. So here's our scatter plot. We're going to calculate the correlation coefficient in StatCrunch. And I would expect it to be positive because there's a positive association. And I would expect it to be closer to 1 than 0. Definitely closer to 1 than 0. Maybe about 0.9. I forget what it's equal to, but that would be my guess, is about 0.9. To calculate the correlation coefficient, everything in this chapter we're going to regression and then linear. And it's just like, let me do that again. I did that kind of quickly. So stat, regression, then simple linear. For this whole chapter, that's what we're going to be going to. And your x variable is speed, your y variable is distance. And I think that's all we need to do. Yeah, so just enter your speed and your distance, as simple as that. And then calculate. So here we have a lot of information. Some of it we're going to discuss in upcoming chapters, but for now, I want to look at the correlation coefficient. It turns out the correlation coefficient is 0.9387. So R is equal to 0.9387. And it's a fairly strong positive correlation coefficient. Okay, so back to our notes. Here's some other scatter plots, and we can take a look at these and just I know the correlation coefficient, so I'm going to tell you, but we're going to talk about each one. So here's a positive association between x and y, and points fall pretty close to a straight line. I don't think I'm going to be able to draw a straight line. That didn't work at all, but if I was able to draw a straight line, the points would fall pretty close to that. And so it turns out that for this example, R is equal to 0.997. It's positive and it's very close to 1. Now if you come over here, you can see there's a lot more scatter around in the scatter plot. And it looks like there's really not much of an association between x and y. This looks fairly random. I don't really pick up any particular pattern. So R would be close to 0, and in this case, R turns out to be 0.021. So essentially 0. There's not much difference between 0 and that. The one down here, I see a negative association, but it's not very strong. There's a lot of scatter around the line. And so in this case, R turns out to be it's negative. That's, we would expect that. 0.404. And coming over here, that's better. I used a different tool. Okay, there's actual straight line. Here we have a negative association. However, it's a little bit stronger than this one. The points are closer to a straight line. And it turns out for this one, and it's negative, so R turns out to be negative 0.63. Okay, so you're not going to have to guess very much. We're going to use calculators or computers to guess the correlation coefficient. The other one thing I just want to talk about before we end this video is correlation and causation. And there's a tendency to conclude that if two variables have a strong association, that one variable causes the other. And this isn't true. We don't know that if we have an observational study. It could be that there's other variables that are causing the changes. So there's a third variable that might be affecting both of the variables. And that third variable is called a lurking variable. Sometimes it's also sometimes called the confounding variable. So I'll go ahead and write that. I think the book mostly uses lurking though. Then you can kind of picture a variable lurking in the lurking outside of the analysis. Okay, so here's one example, and hopefully you'll do some more in class. In the summer, ice cream sales goes up, and so does the number of drownings. And so there's a positive association between ice cream sales and number of drownings. So on a scatter plot, you would see a positive association. So the question is, does this mean that if we limited ice cream sales, we would limit the number of drownings? And the answer is no, because intuitively we know that ice cream sales don't cause drowning. So okay, so there's an association between the two variables, but we can't say there's a cause and effect association. One doesn't cause the other, and that's because they're lurking variables. And one lurking variable would be hot weather is increasing drownings. because more people swim, and also causing an increase in ice cream sales. Okay, so hot weather or temperature would be considered a lurking variable here. All right, see you later.